All right, so this lesson we're going to understand thermal energy, heat, and temperature. So we start off with asking the question, what is thermal energy? And you can see our definition here is thermal energy is the total kinetic energy of moving particles in matter. Now, because all matter has moving particles, that tells us all matter is going to have thermal energy. Even cold objects have thermal energy. So ice cream, here we have a scene from one of the hottest places in the United States, Death Valley, California. Whether it's hot or cold, all matter is going to have thermal energy. The more particle motion an object has, the more thermal energy that object is going to have. So as we have an increase in thermal energy, we're going to have an increase in particle motion. So again, thermal energy is the total kinetic energy of moving particles in matter. And we want to compare that with what temperature is, because a lot of times they get interchanged and they're not exactly the same thing. Notice here that temperature also is measuring the kinetic energy of particles, but it's measuring the average kinetic energy of particles, where thermal energy is measuring the total kinetic energy of particles. So that's how they're different there. Usually we think of more thermal energy if the temperature is higher, but that's not always the case, right? Mass also matters. So remember, mass is a measurement of the amount of matter that something has. So here we have something very cold, an iceberg, but remember cold things have thermal energy, and because this is a fairly big piece of ice, it's going to have quite a bit of thermal energy. Because the more mass something has, the more particles it has, therefore having more total thermal energy. Okay? So we have to compare both temperature, or consider both temperature and mass when we're thinking about how much total energy there is, or how much thermal energy there is. So here we have this massive iceberg that's frozen, and we have a boiling hot cup of coffee. Which is going to have more thermal energy? Well, really it just depends on the relationship, the ratio between how much mass and the temperature. So in this case, probably that iceberg is going to have quite a bit more thermal energy because there's just so much more matter there, so much more mass, a lot more particles that are moving. So a large cool object can have more thermal energy than a small hot object. This gets us into our next topic, which is on heat. So again, they're related, but not all exactly the same. The way we define heat, it is the transfer of thermal energy between substances. So as you can see in this diagram, we have substance A and substance B. Substance A has a higher temperature than substance B. And the way we know that in this chart, not only does it have that symbol for greater than, but you can see the arrows coming off of those particles as longer arrows, indicating it has that greater quantity than in B. And then you can see they've been pressed together, so you can see the direction the heat is going from the hotter object to the object with less energy. So a couple things to make sure that we take away from this is heat is always going to move from warmer to cooler objects. And the faster the particles bump into the slower ones, and that's going to transfer the energy. So faster particles collide into those slower particles, and it's going to lose some of that energy. It's going to speed up that slower particle, and it'll continue to do that until both substances have particles that are moving at the same speed, meaning they both have the same amount of thermal energy, or the same average kinetic energy, or the same temperature. So again, heat is the transfer of thermal energy between substances. Heat always moves from warmer objects to colder objects, and the faster the particles, or the faster particles, they bump into the slower particles, and that's what transfers the energy from the warm to the cold. So here's a little example. We want to know the direction the heat is going to flow when adding ice to a glass of room temperature water. As we know, it always goes from the warmer to the colder, the one with more energy to less energy. So the energy is going to transfer from that water to the ice. So normally we think of the ice is cooling down the drink, but really what's happening is the drink is warming up the ice. Okay? The thermal energy moves from the drink, from the warm water to the colder ice. So the drink cools down because it's losing its thermal energy. It's transferring its thermal energy to the ice. So as the ice is warming up, the drink is losing energy, and that's what makes it have a lower temperature. So again, two main ideas with heat. Heat always moves from warmer to cooler objects, and the faster particles bump into the slower ones, transferring their energy. So heat is the transfer of thermal energy between substances. Now the way we measure it is with this concept of temperature. So temperature is the average kinetic energy of the particles, how much heat is being able to be transferred. And basically what that's showing us is the faster the particles are moving, the higher the temperature is. The slower the particles are moving, the lower the temperature is. Okay? So the way we measure it is with a tool called a thermometer, which I'm sure you're familiar with. And the way it works is there's a liquid inside a glass tube, and as that liquid has more energy, it's going to rise in the tube, because as there's more energy, those particles are moving faster, they're moving farther apart, they're going to expand. So as the temperature increases, that liquid will expand and then therefore rise up the tube, and you can see as you go higher in the tube, the numbers get greater. And then the opposite is true. If that liquid cools off, it loses energy, the particles are going to be moving slower, they're going to contract, and it's going to read a lower number on the scale. There are three specific scales that we want to be familiar with. If you live in the United States, you're probably familiar with Fahrenheit, because that's what we tell the temperature of the weather. We use that for baking. In the metric system uses the Celsius scale, so most other countries use that. A lot of times in our science class we'll use that. There's a third scale that might be new called the Kelvin scale. This is the professional scientists use this. Different reasons for using different scales. We have a couple points that we use as reference, the temperature at which water freezes and the temperature at which water boils. And you can see in both the Kelvin scale and in the Celsius scale, there's 100 units different between water freezing and water boiling. The Fahrenheit scale is a little more archaic than that. So that's why the Celsius and Kelvin scales tend to be used more. The nice thing about the Kelvin scale, there are no negative temperatures. In the Celsius scale, water freezes at 0 degrees, boils at 100 degrees, nice numbers to be able to use mathematically, but when particle motion stops, that's this idea of absolute zero, and that's all the way down at negative 273 degrees Celsius. But you'll notice the Kelvin scale, absolute zero is zero, so there's only positive numbers on the Kelvin scale, and that's one thing that's attractive about those scales. All right, so we want to make sure we know how to convert between scales. Celsius to Kelvin is pretty simple. You simply just add 273 to the Celsius number, and that'll convert it to the Kelvin scale. So if you have 10 degrees Celsius, add 273 to it, now we're working at 283 kelvins. Okay? The Fahrenheit scale is much trickier. We'll create a special lesson just for that, where we'll be able to convert from Fahrenheit to Celsius. So just to wrap this up, remember, thermal energy is the total kinetic energy of particles. Heat is transfer of the thermal energy from one object to another. And temperature is measuring the average kinetic energy of the particles. So they are related, but they're not the same.